It is my great honor to present this report titled Determinant Calculation Methods and Related Topics. In this presentation, we will explore several key topics. First, we will discuss the concept of the determinant, understanding its significance and properties. Next, we will delve into the concepts of minor and cofactor of a matrix, which are essential in the calculation of determinants. Following this, we will examine Sarris's rule, a practical method for determining the determinant of 3x3 matrices. After that, we will explore the Laplace expansion, a general method for calculating the determinant of any square matrix. Finally, we will understand the meaning of determinants, including their geometric and algebraic interpretations. The determinant is a fundamental component in linear algebra. It is a special number associated with a square matrix and can be calculated from its elements. The matrix itself is usually denoted by a capital letter, like A. The determinant of a matrix A is typically represented as DTA, or with two vertical bars surrounding the matrix, written as AA. This notation underscores the distinct and crucial role the determinant plays in the study of linear transformations and matrix theory. In this slide, we will delve into the concept of the minor of a matrix element, an essential aspect of determinant calculations. The minor of an element Aij in a square matrix A is the determinant of the submatrix that remains after removing the ith row and j-mith column of A. For example, given the matrix A shown below, to find the minor M11 of the element A11, we remove the first row and the first column of A, resulting in a 2x2 submatrix. The minor M11 is then the determinant of this submatrix. This submatrix is read column-wise as follows: A22, a 2-3 in the first column, and a 2-3, a 3-3 in the second column. Understanding minors is crucial as they are used to compute cofactors, which play a significant role in determinant expansion and matrix inversion. In this slide, we will discuss the concept of the cofactor of a matrix element, which is closely related to the minor. The cofactor of an element Aij in a square matrix A is calculated by taking the minor of Aij and multiplying it by -1 up to I plus j. For example, given the matrix A shown below, the cofactor Cij of an element Aij is found by taking the minor Mij and multiplying it by -1 up to I plus j. Specifically, for the element A, 1, the cofactor C11 is obtained by taking the minor M11, which is the determinant of the submatrix formed by removing the first row and the first column, and then multiplying it by -1 up to 1 plus 1. Therefore, C11 is equal to the determinant of the submatrix formed by the elements in the second and third rows and columns of A, which are a 2-2, a 2-3, a 3-2, and a 3-3. Understanding cofactors is essential for determinant expansion and matrix inversion, as they are used to construct the adjugate matrix. Let's talk about Sarris's rule, one of the widely used tricks for calculating the determinant of a 3x3 matrix. This rule applies only to 3x3 determinants and not to any other sizes. The rule is as follows. Take the first two columns of the determinant and copy them to the far right, creating a new matrix with 5 columns. Then, calculate the sum of the products of the elements along the main diagonals, downward sloping, and subtract the sum of the products of the elements along the secondary diagonals, upward sloping. By following this method, you can quickly and efficiently determine the determinant of a 3x3 matrix without expanding by minors and cofactors. This rule simplifies the process and is very useful for quick calculations. Now, let's talk about the Laplace expansion, a general formula for calculating the determinant of any square matrix. This method involves expanding the determinant along any row or column of the matrix. When using Laplace expansion, the elements in a chosen row or column are multiplied by their corresponding minors, and then the results are summed up with a sign determined by the position of each element. As shown below, we can expand the determinant along the first row. The determinant is calculated by taking each element in the first row, multiplying it by its corresponding minor, and then applying a sign based on the position of the element. Specifically, if the sum of the row and column indices of an element is odd, the term is taken with a negative sign. Here, a 1-1, a 1-2, and a 1-3 are the elements of the first row. Mij represents the minor of element Aij, which is the determinant of the submatrix formed by removing the ith row and j-mith column. Notice that the sign alternates because a 1, 2 is in the second column of the first row, making the sum of the indices 1 plus 2 equals 3, which is odd, hence the negative sign. And by applying Laplace expansion, you can calculate the determinant of any square matrix, making this method very powerful and widely used in linear algebra. The Laplace expansion method calculates the determinant of a matrix by expanding along any row or column. To use this method, select a row or column, then for each element in that row or column, compute the cofactor by removing the row and column containing the element and determining the determinant of the resulting submatrix. Multiply each element by its corresponding cofactor and sum the products. This sum is the determinant of the original matrix. This method is particularly useful for large matrices, breaking the problem into smaller, more manageable parts. Usually, we will expand along the rows or columns that contain many zeros to minimize the calculation steps. Next, we will explore the significance of the determinant in mathematics. The determinant is not just a numerical value. It carries important geometric meanings. For instance, the determinant of a 2 by 2 matrix represents the area of the parallelogram formed by the matrix's column vectors. For a 3 by 3 matrix, the determinant indicates the volume of the parallelepiped formed by its column vectors. The determinant also measures how much the matrix scales areas or volumes when transforming vectors. A determinant of 0 indicates that the matrix collapses the space into a lower dimension. Next, we will discuss a crucial property of matrices related to their determinants. Specifically, we will explore the condition where the determinant of a matrix is 0. When the determinant of a matrix is 0, it implies that the rows or columns of the matrix are linearly dependent. Linear dependence means that at least one row or column can be expressed as a linear combination of the others. This indicates that the matrix does not have full rank and its rows or columns do not span the entire vector space. For example, here, the determinant of the matrix below is 0, so the rows are certainly linearly dependent as we have observed. Row 3 is the result of adding the first 2 rows together. The determinant is related to many aspects, as we have seen, and it has a special connection to the inverse of a matrix. Specifically, a matrix has an inverse if and only if its determinant is non-zero. This means that for a matrix to be invertible, its determinant must be different from 0. When the determinant is 0, the matrix cannot have an inverse. This property is crucial in various applications, including solving systems of linear equations, transforming geometrical figures, and more. Understanding the determinant helps us determine whether a matrix is invertible, and hence if certain mathematical operations can be performed on it. For example, in this 2 by 2 matrix, the columns 1, 3, and 2, 4 are invertible because their determinant is non-zero. It is essential to master the calculation of determinants because we will encounter this concept again in subsequent mathematics courses. When finding the characteristic polynomial of a matrix, we need to compute the determinant of the matrix formed by A minus lambda I. This process is crucial for determining the eigenvalues from the characteristic polynomial. When finding the characteristic polynomial of a matrix, we need to compute the determinant of the matrix formed by A minus lambda I. This process is crucial for determining the eigenvalues from the characteristic polynomial. Being proficient in calculating determinants will help us solve problems related to eigenvalues and eigenvectors, as well as many other applications in linear algebra and related fields. Since the determinant of the matrix A minus lambda I equals 0, the rows of this matrix are linearly dependent. As a result, the homogeneous system of equations to find the eigenvectors corresponding to the eigenvalues always has infinitely many solutions. We have outlined the method for calculating determinants and highlighted their importance in various linear algebra topics, including eigenvalues, eigenvectors, matrix rank, and linear independence and dependence. I will conclude my lecture here. Thank you for your attention. If you have any questions, please feel free to ask. I am happy to answer them.